All right, today what we want to do is we want to get some practice with integration by substitution. But before we do that, we should continue to emphasize concepts from chapters 5 and 6 related to the meaning of definite integrals. So far, we've done applications to distance traveled and speed. Now let's generalize that to position and velocity. Position and velocity. We could bring acceleration into play as well, but I won't bother. We want to think about position and velocity when the motion that we are trying to model is back and forth motion. So once again, imagine rightward as being the positive direction and leftward as being the negative direction. So if I'm moving to the right, my velocity is positive. If I'm moving to the left, my velocity is negative. And the absolute value of my velocity would be the speed. So let's write down a function here that's now going to represent my velocity as a function of t, not my speed. And I do want to pick something that takes on both positive and negative values here. Like t minus t squared for t between 0 and 2, for example. If you graph this, it's a quadratic with a negative coefficient of t squared. So the graph is going to look like an upside down parabola. And when t is between 0 and 2, it's going to look something about like this. It's going to have horizontal t-intercepts at time 0 and at time 1. And it will be both above and below the axis on the time interval. You can check that with your calculator. You can use typical kinds of units. We could say, for example, this is in meters per second. But you can use feet per second or feet per minute or miles per hour or kilometers per hour. There's lots of different units that could be used. Say it gets down here when t equals 2. I've drawn it reasonably accurately. And let's say we want to have not the distance traveled, but the position. What's my position as a function of time? By the way, this velocity is an instantaneous velocity at any given moment in time. When you plug a number into this function, for example, plug in t equals 0.5, that's telling you at time equals 0.5 seconds, your instantaneous velocity is 0.25 meters per second, a quarter of a meter per second. That's how fast you're going at that moment, that instant in time. If you continued at that same velocity, a quarter of a meter might be about this big. You'd be traveling about this fast, 1001. That's about how fast you'd be going if you continued at that velocity. Now you don't continue at that velocity. Your velocity is changing over time. It's a function of t. In fact, think about it with me here. The fact that the velocity at time 0 is 0 means at the initial moment you're not moving. But right away you start moving to the right because the velocity becomes positive. When t is 1, or 0.5, excuse me, your velocity is 0.25, and that's as high as the velocity goes positively. And at that moment in time, 0.5, you're turning around, you're moving toward, after 0.5, you start slowing down. And at time 1, you turn around, you start going in the negative direction because your velocity became negative. And it's getting more and more negative, so you're speeding up faster and faster. Your speed is getting larger and larger. Does that make intuitive sense? I'm going to assume that my initial position at the starting time at t equals 0 seconds is 0 meters. effectively, when I watch the motion that's back and forth here, I'm saying whatever the starting point is, that's the origin of a number line. So I start at the origin at position 0 at time 0. I move to the right a little bit, then I move to the left and speed up. That's going to make things simpler. It's not that I have to do that. You always have freedom to decide where the origin of your axis is. But it usually makes the most sense to pick the origin at the starting point, at least if you're moving left and right. If it's up-down motion, it might make more sense to put the origin at the ground level. And if you have a ball in your hand and you're throwing it up from your hand, you're going to throw it above ground level at time 0. And then your initial position would be some positive number of meters. Let's go ahead and continue to use the letter S for position now instead of distance traveled. And let's continue to call it capital F. And it will be an antiderivative of little f. This is going to be the position at time 0, or at time t, excuse me, in meters. And this assumption means capital F of 0 equals 0. Because I'm starting the position at time 0, the position itself is the same as the change in position, which I could call delta F. If I start somewhere other than position 0, say throwing a ball up with my hand as I'm standing here, and I let the ball go up and then come down and hit the ground, the change in position is not the same as the actual position if the ground is position 0. If the ground is position 0 and I'm holding this ball, say 2 meters above the ground to start with, or maybe 1.5 meters, and I throw it upwards and it comes down and hits the ground, its change in position is negative because it ended lower than it started. But the final position is 0 because the ground is height 0. But again, because this is true, then that's true. F of t is the same as the change in f, because f of 0 is 0. It's the change in position that always equals the integral of the velocity. Generally not the position itself. The integral gives the change in position. The integral of the velocity. I'm purposely being really careful here about what I write. Like on Wednesday, I do want to write this as a definite integral with a variable upper limit of integration. 0 to t. This is really important to me that we get this across conceptually, because you have to do with this if you're going to understand what our book calls at the end of chapter 6, the second fundamental theorem of calculus. But if you do this, if you make the variable the upper limit of the integral, you should use a different letter down here like tau, say. But it doesn't have to be tau. It could be u, it could be v, it could be w. Just don't use a t. I guess don't use an f either or a d, because that would be confusing. Let's go ahead and evaluate this integral. What's f of tau? Well, here's f of t. Just replace those t's with taus. Tau minus tau squared, d tau. With the first FTC, first fundamental theorem of calculus from chapter 5, we can evaluate that integral by finding an antiderivative. Find an antiderivative of tau minus tau squared. It would be 1/2 tau squared minus 1/3 tau cubed. Tau goes from 0 to t. And this notation again means plug in the top number, t in this case, and subtract what you get when you plug in the bottom number. This becomes 1/2 t squared minus 1/3 t cubed minus 1/2 times 0 squared minus 1/3 times 0 cubed, which is, of course, 0. So this simplifies to 1/2 t squared minus 1/3 t cubed. And then you say to yourself, did I really have to do all that? Couldn't I have just jumped to the answer right from here to there? The answer is yes, you could have. Find the indefinite integral of t minus t squared. You'd get 1/2 t squared minus 1/3 t cubed plus c. But then you take c to be 0 because you want f of 0 to be 0 here, capital F of 0. And you'd get the exact same answer. So why go through all this stuff? It's important for a couple different reasons. It's important that you realize that conceptually speaking, this is all true. You can do this. And that's related to also the second fundamental theorem of calculus at the end of chapter 6, which I will write down in a second here. More importantly, perhaps, is that sometimes you have to think of it just as an integral because you can't apply the first FTC. Because to apply the first FTC, you need to be able to find an antiderivative. And you've seen already, we've seen with Fresnel S and Fresnel C, for example, there are little f's that you can't really integrate without giving them a new name. They're not elementary functions. They're not polynomials. They're not rational functions. They're not trig functions. They're not exponential functions. They're not logarithms. They're not any finite combination of those things. So you would either have to give it a new name or use somebody else's name that they are already given it and use technology to approximate it. Or if nobody's given a name to an antiderivative of little f, you'd have to actually compute capital F numerically by numerical integration. That's the point of numerical integration, when you can't use the first FTC. And there's many practical situations where you can't, unfortunately. It's great when you can, but sometimes you can't. What does the second fundamental theorem of calculus say in this situation? Well, actually, let me do a more general situation. It says that if you differentiate an integral where the variable for the function of t in this case is in the upper limit of the integral, and it really doesn't matter what the lower limit is, I'll call it a. For our example, a is 0. Little f of tau d tau, say, it's like the d dt and the integral sign cancel. Poof, by magic, they're gone. It's not magic, but it feels like magic. And you're left with the little f function. But do not call its variable tau. You want it to match these two variables that match each other, t. This is the essence of the second fundamental theorem of calculus, second FTC in chapter 6. And it's really important that you get this for this class, that you can do this. I don't mean to understand why it works right now. Hopefully we'll have a little time next week to understand intuitively why it works. But just to understand that this is true is a pretty big part of this course. Also, perhaps next week, if we have time, we will use the second fundamental theorem of calculus to prove the first fundamental theorem of calculus, which makes you think maybe we should switch their names around. And in fact, many books do. Many books call this the first fundamental theorem of calculus and this the second one, because it's easier to use this one to prove that one than the other way around. But that begs a question: how do you prove this one? That proof, that argument is in the book at the end of chapter 6. We won't do a full proof, but we'll sort of try to get the idea of it. And yes, we do proofs in here sometimes. It's not a big point of emphasis, but sometimes it's worth spending time writing things down carefully, getting our logical thinking down carefully on paper. that helps you think not just in math, but more broadly in life, on the job, maybe when you're tutoring your kids or homeschooling your kids. Reasoning is really useful, actually. It's good to get practice. Can I clarify anything here? Please let me know if I can clarify anything. I know this is kind of abstract, though it is a particular example. We can still think about this in terms of areas, accumulated areas. However, because the graph goes below the axis, we need to count areas between the graph and the axis when it's below negatively toward the integral. And that should make intuitive sense if you think about the application. Actually, I'm going to get in Mathematica, I'm going to animate this with vertical motion. I'm going to, on Mathematica, show you a dot starting at the origin on the vertical axis, whose velocity is going to be given by this function. So it's going to start at rest. And then when time becomes positive, it's going to move upwards. It's going to have a positive velocity, a maximum positive velocity at time 0.5. Then it'll slow down, though it's still going up. At time 1, it's going to turn around and start going down because the velocity is negative. And because this area right here is bigger than this area right here, in the end, by the time we get to time 2, the change in position will be negative. The dot will be below the axis. What will that change in position be, which is again the same as the actual position, since we're starting at the origin? It would be capital F of 2. Here's the formula for capital F. That'll be 1/2 times 2 squared, plugging in here, minus 1/3 times 2 cubed. And that will be 2 minus 8/3, which is negative 2/3 meters, is the change in position over 2 seconds. It's also the same as the actual position since I started at position 0. Let's see that in Mathematica here now. You do not need to know this code for the moment. Again, I may test you on some basic things about Mathematica, but this is fairly complicated. Don't worry about what it means. Change this to a 1 here. Let me change this to a negative 1 as well. So that black dot is going to be the object, say the ball, that goes up and then comes back down. And I guess the origin's not ground level here because it's going to go negative. Which graph, red or blue, is the position? The blue one, yeah. The second coordinate of the blue graph at any moment in time gives you the height, the position of the black dot. Blue is capital F. Red is little f. Red was the original velocity function, t minus t squared. The blue is the capital F that we found, 1/2 t squared minus 1/3 t cubed. Yep, the object goes up, turns around, comes down. And the change in position by the time we get to time 2 is negative 2/3, which is negative 0.6 repeating, which is happening right about, oops, got stuck there, right about now. It ended up 2/3 of a meter below where it started.
Why is it kind of backup like that?
It's just restarting the animation when it does that.
No. When you play it,
Mhm.
like they stay right, the 2 tips stay right vertical, but then the red one skips a bit.
Yeah, that's some sort of Mathematica error. It's happening. I think I can fix it if I do plot range all. I'm not sure why it's happening. It's not ideal. I think this will do better.